Hello everyone, I'm Shaofei Huang from the Institute of Information Engineering, Chinese Academy of Sciences. Today I'm going to introduce our work named Anchor3DLane, learning to regress 3D anchors from monocular 3D lane detection. Here is the preview of our paper. In this paper, we focus on monocular 3D lane detection to get rid of BEV representations while still maintaining superior performances. We define lane anchors in 3D space and proposed a BEV-free method named Anchor3DLane to predict 3D lanes directly from FV images. The 3D anchors are projected to the FV features to extract accurate anchor features for prediction. In addition, we also develop a global optimization method to make use of the equal width property between lanes for lateral adjustment of predictions. We first explain the motivation of our work. Mainstream 3D lane detection methods are based on the BEV perspective. They first warp images of features from FV space to BEV with IPM, and then detect 2D lanes from the BEV features. They also estimate each lane point's height to project BEV lanes back into 3D space. There are two limitations of these methods. First, IPM relies on the assumption of flat ground, which does not hold true in the cases of uphill or downhill. Second, some useful height and context information about the road surface is lost after IPM. Such kind of information loss will harm the estimation of 3D coordinates. To this end, some methods seek to get rid of BEV and predict 3D lane coordinates from FV images directly. It decomposes the 3D lane detection task into 2D lane segmentation and depth estimation. The segmented 2D lane maps are projected back to 3D space with the estimated depth. This method lacks structural representation of 3D lanes, and its performance still lags behind the BEV-based methods. In this work, we proposed a BEV-free method named Anchor3DLane to predict 3D lanes directly from FV images. We define 3D lane anchors as the structural representation of 3D lanes. The 3D anchors are projected to the FV features to sample their features with the assistance of camera parameters. Unlike BEV-based methods, such projection and sampling operations retain range context information. Besides, they also enable the extension to iterative regression and multi-frame information propagation. The 3D lanes and 3D anchors are represented in the right-handed ground coordinate system, whose origin is set on the road surface right below the camera center. Each 3D lane or anchor is described by n 3D points uniformly sampled along the y-axis. Each lane point is represented by its x, y, and z coordinates and a bool value indicating its visibility. For the 3D anchor, it is defined as a ray starting from xx 0, 0, with pitch equals to theta and yaw equals to phi. Its points are also represented by x, y, and z coordinates. Here's the overall architecture of our Anchor3DLane. Given an FV image as input, it is first fed into a backbone network and a transformer there to extract feature f. We sample endpoints from each 3D anchor and project them to f with the assistance of camera parameters to obtain features of these projected points. The anchor features is thus acquired by concatenating features of endpoints along the channel. After that, a classification head and a regression head are appended after the anchor features to acquire their classification probabilities, XZ offsets, and visibilities of endpoints. 3D proposals are generated by adding XZ offsets with XZ coordinates of anchor points. The generated proposals can also be used as curve anchors for iterative regression. Our Anchor3DLane is trained with a classification loss and a regression loss. We adopt focal loss for classification and L1 losses for anchor regression. Anchor3DLane can be further extended to multi-frame information propagation. Given the poses between two frames, anchor points can be projected to the previous frame to sample anchor features from the corresponding feature map. After that, cross-frame attention is applied to anchor features from multiple frames for temporal context modeling. We further leverage the geometry property of 3D lanes that they are nearly parallel with each other in most cases. We formulate this property as an equal weight constraint to adjust the x-coordinates of lane predictions. Given the x-coordinates of two lanes, we first calculate the distance between point pairs and constrain distances to be consistent with each other. To avoid the adjusted points being too far away from their original locations, we also add a regularization term. We run extensive ability studies of different components. In Table 1, it shows sampling anchor features directly from FE features achieves better performances. By realizing predictions before and after EWC adjustment, we can observe that predictions appear to be more parallel with each other. We compare our method with previous SOTA 3D lane detection methods on 3 benchmarks, including Apollo Sim, OpenLane, and ONCE 3D lane. Our method achieves better performances on all the 3 benchmarks. As shown in these tables, our single-stage Anchor 3D lane already achieves better performances compared with previous method. Together with iterative regression and multi-frame information aggregation, the performances of our methods can be further improved. Here shows a qualitative comparison between our method and other methods. Our code has already been released in GitHub. That's the overview of our work. Thanks for listening.